Hello and welcome to Honors Function. In this video, we're going to learn about rational functions. A rational function is to a polynomial what a rational number is to an integer. A rational number is the ratio of two integers. A rational function is the ratio of two polynomials. Let's begin. So if you take two polynomials, for example p and d, and if you do their ratio, you have a rational function. So p has a degree, d has a degree, but f, we don't say that a rational function has a degree. Okay, f doesn't have a degree. The degrees of p and d will play a role in the end behavior of the function. So how do we study a rational function? We want to study the rational function in order to graph it, okay? So the whole idea is to be able to graph fairly precisely the rational function. I'm going to suggest some steps that you can take, and some of them, you don't have to take them in the order I will suggest, okay? So here we go. First, you should be looking for the domain of the function. This is something you know how to do. We have been looking for domains of functions for a while now. So you need to solve the equation d of x equal to 0, and the domain is all real number except all the x's that will make d of x equal to 0. This is going to be your domain, and you can use interval notation to write it if you want to. Okay? The second point that I wrote right here, I'm going to put that in parentheses because symmetry of a rational function, it doesn't happen often. It would have to be really striking, like the function would have to have only even coefficient to study the symmetry of right here. For example, this one. Okay, so I know that in this case right away f of negative x equals f of x. Okay, and so I would have a symmetry through the y-axis because the function is even. I hope you remember even and odd, but that doesn't happen very often. Most of the time a rational function will not have any symmetry, so this step we can forget about it. Okay, this is a good step to keep in mind all the time whenever you study a function, but it's okay if you don't see it right away. Alright, determine the x-intercept of the graph. So the x-intercept of the graph, for that you need to solve the equation f of x equal to 0, right? Now, f of x is p of x over d of x, right? So when is a fraction equal to 0? When the numerator is 0. So f of x equal to 0 is equivalent to p of x equal to 0. Okay? The solutions to this equation will give you the x-intercept if they are in the domain. Therefore, the other thing you want to make sure of, you remember that stands for and, is that d of x is not 0, okay? You want to be in the domain. So the solution to this equation, or rather the solution to this condition, will give you the x-intercept of the graph, also called the zeros of the function, alright? Y-intercept, number 4, y-intercept, well, that's super easy. You plug 0 in for x, that's it. That's going to be your y-intercept. Now, of course, the y-intercept should be a point. So here we go. All right. Vertical asymptotes. So why would a rational function have a vertical asymptote? At a vertical asymptote, the function is undefined, right? The function is undefined. Undefined. Now, the places where the function is undefined comes from the denominator. Okay, so we've already solved that. Isn't it the solution to the equation d of x equal to 0, right? So suppose, for example, suppose that a is a solution. So suppose that d of a is actually equal to 0. So do we have that x equals a is a vertical asymptote? Is it a vertical asymptote? Not necessarily. Not necessarily. It's a vertical asymptote if a is not a root of the numerator. Okay? If a is not a solution, so you want to have p of a not 0, and in this case x equals a would be a vertical asymptote. So let me erase all of that and give you the substance of a vertical asymptote. Alright, so vertical asymptotes, you want d of x equal to 0, okay? And at the same time, you want to make sure that p of x is not 0, okay? And there you have the condition for vertical asymptotes. So if you look at the other one before, p of x equal to 0 and the numerator 0 and the denominator not 0, that's an x-intercept, right? And then the denominator 0 and the numerator not 0, that's a vertical asymptote, okay? All right, next point, the hole in the graph. So what's a hole in the graph? Well, a hole in the graph is going to be the places where d of x is equal to 0 and p of x is also equal to 0. Okay, so when both of them are equal to 0, you will have a hole in the graph. How does it work? Let me show you a quick example. Suppose we take the function y equals x squared plus 2x minus 3 over x minus 1. So this function, the first thing I do whenever I have a rational function, I factor it, right? So you can factor that as x plus 3x minus 1, right, over x minus 1. And there you see right away that x minus 1 and x minus 1 is a factor of the numerator and denominator. It's a 0 of both. So this function is going to be exactly the same as x plus 3, which is very easy to graph, right? If you see this, you're like, oh, how do I graph that? But then you know how to graph x plus 3. The only difference is that this function is not defined at 1, okay? So at 1, what do you have? A hole. That's it. I think we've seen that when we looked at domains of functions, okay? All right, and finally, and this is what I'm going to spend some time in this video to study, the horizontal asymptotes. Now, I don't like this denomination too much. I prefer to say asymptotic behavior, okay? Why? Because you don't have necessarily a horizontal asymptote. An asymptote is not necessarily a line. For example, I can have a function whose graph, this is not the function one I'm about to draw. I'm about to draw the asymptote. This is a parabola, right? Let's suppose it's a parabola, okay? We can have a function that has this graph as asymptote. For example, it could do something like that, the function. And then it goes there, and then it comes close to the asymptote. And on the other side right here, it could do this right here. Now, in red, that could be the function, okay? And you can see the asymptote is not necessarily a line. If you say horizontal asymptote, you think of a horizontal line. That's why I prefer asymptotic behavior. So how do we look for the asymptotic behavior? What do we do here? Well, we want to know what's going on when x grows very large or very small, right? Where are the f of x? Where does f of x go? Why does it approach us? Okay, so usually what we're going to do, we're going to define an equivalence for f of x at plus or minus infinity with a function g of x that is much simpler. Okay, this is the idea of the asymptote. You have an equivalence of f of x with a function that is much simpler. We've already done it, right? You remember polynomial, for example, 2x4 plus 5x cubed minus x squared plus 2. This is equivalent at plus or minus infinity. This is equivalent to 2x4, right? And this is much simpler. This is the asymptote of the function. It's a graph towards which this function is coming very close, okay? All right, so what's going on for rational function? Let's begin looking at the different cases. So let's take a rational function, p over d, but let's write p and d in the standard form. So p is a polynomial of degree n, while d is a polynomial of degree q. We want to know where the output of the function are as x approaches plus or minus infinity. Well, we know what's going on at the top, right? As x approaches plus or minus infinity, the polynomial at the numerator is equivalent to an xn. We know what's going on at the bottom. The polynomial at the denominator is equivalent to bq xq. We've already seen that when we looked at polynomial. Therefore, the function f of x, the rational function f of x, is going to be equivalent to an xn over bq xq. Let me rewrite that as an over bq times xn over xq. Okay, and this is what we need to study. We need to study this ratio, because there's no variable here, right? This is not a function of x. No x is there. We need to study the ratio as x approaches plus or minus infinity. This is not so difficult. We need to study three cases. The case when the numerator has a smaller degree than the denominator, the case when the numerator has the same degree as the denominator, and the case when the numerator has a larger degree than the denominator. Okay, and this is what you will have to do whenever you want to look at the end behavior of a rational function. You will have to decide which case you're in according to the degree of the numerator and the denominator. Let's begin. Okay, first case, sometimes students call it bottom heavy, okay, because the denominator has a larger degree than the numerator. I'm not a fan of this denomination, but anyway, I'm just putting it out there. All right, so bottom heavy rational function. You can write these as, so n is smaller than q, right? So you can write these as an over bq times 1. I'm dividing both sides by xn over x to the power of q minus n. And if q is greater than n, then this power is positive, right? So basically, we're looking at something that looks like either 1 over x or 1 over x squared or 1 over x cubed, right? Basically, it's like a 1 over x to the, let's call that p, okay? And we know where this goes as x approaches plus or minus infinity. It doesn't matter what the power is. These will go to 0, right? Because the bottom is going to get very, very large, and therefore if you take the reciprocal of the bottom, it's going to get very, very small. Now, we're going to have to be careful if it's a 0 plus or a 0 minus, right? We're going to have to keep track of the sign, but that's a little detail. The function will approach 0. Therefore, we have our end behavior. F of x is actually equivalent to 0 at plus or minus infinity. Another way of saying that is the limit of f of x as x approaches plus or minus infinity equals 0. Another way to say that is that you have a horizontal asymptote, and the equation of the asymptote is y equals 0. Okay, so there are three ways to say that, all equivalent. Horizontal asymptote, limit, or this equivalence right here. Let's look at the second case now. All right, this time the powers, the degrees, are the same. So what happened to this ratio right here? Well, if the degrees are the same, this is just an over bq, right? You can simplify xn and xq because it's the same thing, x2 over x2, x5 over x5, right? And so you're left with something that is not a function of x. So as x approaches plus or minus infinity, this doesn't change. It's a constant. It's still an over bq. Therefore, f of x is equivalent to an over bq as x approaches plus or minus infinity. This is the end behavior of the function. We can write limit of f of x as x approaches plus or minus infinity is an over bq. We can also express this by saying that there is a horizontal asymptote, and the equation is y equals an over bq. So again, these three writings are completely equivalent. Okay, that's the second case. Last case now. So last case, a top heavy. This is what sometimes students call a top heavy rational function. Okay, so top heavy, we can write this as an over bq times x to the n minus q, and here n minus q is positive, right? So what are we dealing with here? We're dealing with something that looks like either x or x squared or x cubed or x4. We've seen this kind of behavior when we looked at polynomial, right? We've seen this kind of end behavior when we looked at polynomial. So in this case, it's going to go towards either plus or minus infinity, depending of the degree, and depending if x goes to plus or minus infinity itself. Okay, so this case is a little bit more complicated. f of x here, f of x, the limit of f of x as x approaches plus or minus infinity is plus or minus infinity. Okay, so this is not very satisfying. We still would like to find the asymptote. Is there an asymptote? Yes, there is an asymptote, and to do it you have to do the long division. Suppose p of x over d of x, you can write it as q of x, the quotient, plus the remainder divided by d of x. We know this is how we can present the result of the long division, right? Then the equation of the asymptote is y equals q of x, okay? This is a bottom heavy rational function, so it's going to go towards 0, okay? As x approaches plus or minus infinity, it's going to go towards 0, and therefore p of x over d of x will go towards the quotient right here. The quotient is going to be your asymptotic behavior, and so the quotient can be a line. Maybe it's going to be mx plus d, maybe it's going to be ax squared plus bx plus c, or maybe it's going to be ax cubed plus bx squared plus cx plus d. I mean, it's going to be a polynomial function, okay? So it's no longer horizontal asymptote necessarily. Let's quickly check 3 examples I've completed myself in the notes, and then we'll do an example together, okay? All right, here is the first example. Here is a bottom heavy function, right? So the leading terms for both of them are 3x over x cubed, so it's 3 over x squared. As x approaches plus or minus infinity, this will go towards 0, okay? And you can see that the x-axis, y equals 0, is the asymptote of the graph in red, okay? Very quickly, right? You don't have to go to plus or minus infinity. Look, it's already true at like -8 and 10. The graphs are completely on top of each other. Let's look at the second example. So, second example now, look at these 2 degrees. They're the same, okay? So the function is going to behave like 4 over 6 as x approaches plus or minus infinity. 4 over 6 is 2/3. This is the equation of the horizontal asymptote, and you can see this is 1 right here. In blue you have the line y equals 2/3 and the graph coming very, very close to the line. And again, you don't have to be very far for that to be true, okay? Finally, the last case. So here is a top heavy function. The difference of degree is 1, right? If I do 2x cubed over x squared, I'll find 2x, right? So the function is going to behave like 2x, but be careful. This is not the asymptote. It's not the asymptote. If you want to find the asymptote, you need to do long division. It's going to behave like 2x, but it's not the equation of the asymptote. Okay, so if you do the long division, you're going to find 2x minus 3 for the quotient, and look at the line 2x minus 3. It is the equation of the asymptotes. Now, in the second example here, I'm taking a difference of degree of 2, right? This is a degree 3 and this is degree 1, so the difference is 2. Therefore, the asymptote will behave like x squared. If you do the long division, you're going to find the equation of the asymptote, x squared plus 2x plus 3, and you can see that the blue graph is indeed asymptote to the red. Let's go over an example. I'm going to do example 2, you will do example 1 and example 3. I'm going to give you some indication about example 1 though. In example 1, please try the root x equals 2 for the denominator. You need to factor the denominator, right? You need to factor it. So try x equals 2. And after that you should be able to factor it completely. I don't need to give you any indication for the top, it's pretty simple. Let me go over example 2. Alright, the first thing I do whenever I have to study a rational function is that I will try to factor top and bottom. The bottom, that's super easy. The top, look at the top, you got x cubed plus 3x squared minus 4. How can we factor that? Well, pay attention to the coefficient. 1 plus 3 minus 4, right? What is 1 plus 3 minus 4? That is 0, right? So if you don't change the coefficient, you have a 0. Therefore, I know that x equals 1 is a 0. Okay, x equals 1 is what happened when you don't change the coefficient. So let me break it with 1. So 1, 3, don't forget 0 and negative 4 right here. So what do we have? 1, 1, 4, 4, 4, 4, 0. Okay, so let's factor the rational function. f of x is equal to what? X minus 1 times x squared plus 4x plus 4 divided by, and the bottom, that's easy to factor, it's x minus 1 times x minus 2. Please do not simplify that. Do not simplify it yet. We haven't studied it, okay? So let me finish factoring it. So we have x minus 1 times x plus 2 squared, right? This is a square right here, over x minus 1 times x minus 2. Again, it is essential that you do not simplify this rational function right here, okay? So now let's look at domain. Domain. The domain of f, well, that's easy, right? It's everything that doesn't make the denominator equal to 0, so all real number except 1 and 2. And this is why you cannot simplify it, because you would have eliminated 1 and you wouldn't know that 1 is not in the domain. Parity, no, there's no parity. X-intercept, so let me go with the x-intercept. X-intercept is the numerator, so now I can simplify, okay? Let me simplify. Numerator equal to 0, but not the denominator, so there's only 1, and it's at negative 2, right? If x equals negative 2, x plus 2 is 0. So x equals negative 2, it makes a numerator equal to 0, so the x-intercept is going to be negative 2, 0. That's it, I got it. Y-intercept, for that, I'm going to look at the given expression. This goes, it's negative 4 over 2. Y-intercept is negative 4 over 2, so it's 0, negative 2. Okay, next, hole in the graph. Do you have any hole in the graph? Yes. See the simplification right here? At 1, you have a hole in the graph. What's the y-coordinate of the hole? Well, now if you look at the simplified expression, x plus 2 squared over x minus 2, if you look at the simplified expression, it's defined at x equals 1, right? Therefore, you can find the y-coordinate of the hole just like that. So it is 1 plus 2, 3, so 3 squared over 1 minus 2, so it is negative 9. The hole in the graph has a coordinate 1, negative 9. Am I missing something here? What's the next step? Okay, vertical asymptotes. I was forgetting vertical asymptotes. Vertical asymptotes, denominator equal to 0, but not the numerator. Okay, not the numerator. So there's only one place. It's right here, x equals 2. Vertical asymptote is going to be x equals 2. And finally, asymptotic behavior. Okay, so asymptotic, and that I mean as x approaches plus or minus infinity. Okay, behavior as x approaches plus or minus infinity, and behavior, I guess we should say, and behavior. So let's see what kind of case we're in. We are in the case, we have a top heavy. The difference of degree is actually 1. Okay, so I know it's going to be a slanted asymptote, a slanted line. Let's do the division. Let's do the long division to find the equation. So I have x squared minus 3x plus 2 into x cubed plus 3x squared minus 4. Now, the thing is, you don't need to finish the long division. As soon as you have the quotient, you're done. So how many x squared into x cubed? Well, 1, right? X times x squared is x cubed, so negative x cubed. X times negative 3x squared is negative 3x squared, so plus 3x squared, right? I changed my sign right away. And x times 2, I don't need to do this one right here, plus 2x or minus 2x. I don't need to do this one right here, I'll show you why. This will cancel, right? The x cube will cancel. I have 6x squared. And right here, I don't need to go further. I don't need to write minus 2x minus 4 because I have the second term. It's 6. So right here, I have plus 6 and I'm done. That's the equation. So y equals x plus 6. Okay, this is the equation of the asymptotes. Okay, let's graph everything now, right? Let's graph everything that we found. All right, so what do we have? X-intercept, negative 2, 0. Here we go. Here's my x-intercept right there. 0, negative 2 is a y-intercept right here. 0, negative 2 is a y-intercept. 1, negative 9 is my hole. 1, negative 9. I have a hole right here. 1, negative 9 is my hole. x equals 2 is the equation of the vertical asymptote. X equals 2, I have a vertical asymptote right here. Okay. And finally, y equals x plus 6. So x plus 6, it goes by 2, right? 2, 4, 6, yeah, right here. And then it's just x. So here we go. So from here, I'm graphing something with a slope of 1 right here. I should use a straight edge, okay? All right, now, careful guys. Careful, careful, careful. You see this right here? You see this? What does it mean? It means that at -2, the graph is going to bounce on the axis. The graph is going to bounce on the axis. So how does it go? So right here, it bounces on the axis, and then it's got to come close to the asymptote, right? So here we go. Then right here, it's got to cross there. Then it goes down to the hole right here. And then what? You're going to go back up? No, you're not going to go back up because you don't have an x-intercept here, right? So you don't go back up. You just go towards your asymptote right here. That's it. Now what's going on? This is in this portion of the plane, right? Now what's going on in this portion of the plane? Well, you have a vertical asymptote right here and a slant asymptote. So you could do something like this, or you could do something like this, right? Which one is it? Well, it's not this one because you don't have an x-intercept here, right? Therefore, it is necessarily this one right here. Now, how low does it go? I don't know. Okay, it's okay if you do this, it's okay if you do this. I don't know how low does it go. This is what you study in calculus. But that's the graph of the function, okay? So we're gonna practice this kind of graphing a lot. This is not the easiest thing, but after a little bit, after you've done a couple, you'll be fine with it. Let's do one last type of problem. So in the last series of problem, and I won't have time to go over the percent relative error, I want to find an approximation for this function at -87, at 217, and the last one is at -150. Well, what are we going to do? We're going to do the asymptotic behavior. We're going to do the asymptotic behavior, okay? For example, number 4 right here, it's a bottom heavy function, so I know that f of x is going to be about 0, okay, at plus or minus infinity. So actually f of x, f of -87 is about equal to 0. I will let you look at the percent relative error on this one. You know the formula, right? What about number 5, sorry. What about number 5? Well, they have the same degree, right? So I know that f of 217 is going to be really, really close to 6 over -4, which is -3/2. Very, very close. How close? Check out the percent relative error. Please complete number 6. You're going to need the example that I've done. I did it myself. So check it out. This function is a function I've covered before. You do have the equation of the asymptotes. Okay? All right. Thank you for watching.